Right, hello Year 8. So today we are going to be looking at a new topic, and topic is wave and wave properties. So that is your title. And the first thing I would like you to do is have a go at this starter activity. So draw a wave. Can you label any parts, and can you give any examples of waves, or things that travel as waves? Okay, so pause the video now, do that. For question 2, it might be a good idea to leave some space so you can label it up a bit later. Okay, so welcome back. So today we're going to learn what a wave is, compare the properties of transverse and longitudinal waves, and define the words wavelength, amplitude, frequency, and time periods. Okay, so firstly, there are lots of different waves. There are ultrasound waves. These are high frequency waves that reflect off the baby's tissue inside of womb, and you can see how we can use that. So essentially a sound wave going in, hitting soft tissue and bouncing back out, and that echo being detected. Seismic waves radiate from an earthquake. So when you get an earthquake, you get the energy rippling out as waves from the focus. A couple of other examples for you. There's light. Light can be split as a wave. There are sound waves that we know about. Microwaves, which are used in a microwave oven to cook food. You can see here infrared, an image of a person, and also X-rays and gamma rays, which are given off by some objects in space, like black holes. So there are lots of different waves, but we need to be able to describe what a wave is. So, firstly, can you write down these two words, transverse and longitudinal? So I'm just going to pause the video and do that now, please. Okay, so this is the definition of a wave, and this must be in your book, and I'd suggest you circle it or make it really clear and stand out. Waves can transfer energy, but not matter, stuff. They involve vibrations called oscillations. Okay, so waves can transfer energy, but not stuff. Okay, so let's have a closer look at what that means. So you're all probably familiar with an example of a Mexican wave in a stadium. Okay, think about what's happening. Are the people actually moving? Okay, so when they all jump up and lift their hands up like this, are the people actually physically moving from their seats? The answer, of course, is no. What they're doing is they're basically allowing the wave to move through them or past them, okay, by throwing their hands up in the air. But they're not like they're physically getting out of their seat. Say, for example, this person here is not like, or this person here, they're not like they're getting out of their seat and running around the stadium. They're not moving, okay? And this is a really good example of how a wave actually works, okay? So the first thing I would like you to do is, in assignment, there is a copy of this video clip. Okay, I want you to click on that link, and then I would like you to pause this video and fill in this table. So you need to draw this table in your book. So a transverse wave and a longitudinal wave. So pause the video, please, and do that now. Okay, so welcome back. So we can start to fill this in. I'll help you with some of these as we go. But essentially, a transverse wave, the oscillations or the movement goes up and down. So basically at right angles. So if you can imagine, the energy is moving up and down, even though the wave is sort of actually moving along this way. Okay, so the wave might be moving along like that, but the energy goes up and down as it goes along like that. Okay, now with this one, a longitudinal wave, the oscillations, so the movements are not up and down, but back and forth as the wave moves along. So the wave might be going along in this direction, but what you get is a sort of backwards forwards movement. So basically, it's like particles get compressed and like here and here and here. Let's move that down so you can actually see it. So compressed, so squished together, but then spread out here and here. Okay, So think of them as being sort of compressed and spread for longitudinal, but up and down for transverse. Okay, so the rest of these you can fill in yourself. So examples, okay. You should have got that from the video. Things like light would be in here, but sound would be over here. But there are other examples I want you to get. And then I want you to think of a way of remembering which is transverse and a description of longitudinal. Okay, so if you didn't quite finish filling this in, pause the video once more and fill that in, please. Okay, welcome back. So just to finish that off, examples of transverse waves would be water ripples, light, all forms of light, I should say, so not just light, but radio waves, microwaves, things like that. You could do it on a rope or slinky, like they've got in the picture here. Some kind of earthquake waves are also transverse. And as I said, transverse waves look like this. So good descriptions. The oscillations are perpendicular, so basically at right angles to the direction of energy transfer. Okay, so what does that mean? It means that the wave is going this way, but the oscillations, the movements, as you can see, are up and down, like that. Okay, so that is what this definition actually means. Okay, so a couple of other properties that you need to know about transverse waves. Okay, now bear these in mind because you will need them to do the assignment a bit later. So there is the peak of the wave. That's the very top of the wave. We call the peak, or sometimes we call it the crest. And then at the bottom, there is the trough. It looks like a trough, like a pig's trough that you might eat out of, or pigs eat out of. But there are other parts of the wave that you need to know about. For example, if you want to know that, then you'd very simply get a ruler and measure it. So the distance from one peak to the same point, or the next peak, I suppose, we call that the wave length, and that's measured in meters. Okay, now usually you measure it from peak to peak, but as you can see, just as easy to measure it from trough to trough. It's the same distance. In fact, you can measure it at any point, even halfway up, because look, here it's halfway going down, goes up, and then halfway down again, and it's the same length. So the wavelength is the point on one wave to the same point on the next wave, but the easiest place to measure it is from there. Okay, now a couple other things you need to know. You need to know about the amplitude. Now the amplitude is the height of the wave. Okay, now some people think that that is the height of the wave. That is wrong. The height of the wave is from the middle to the top, or once again from the middle to the bottom, which as you can see is about the same. So the amplitude is the height of the wave from the middle to the bottom or from the middle to the top. Okay, so just need to have a few little labels here. So this is the wave length. Okay, and this one is, oops, just move that slightly, is the amplitude. Okay, essentially both of these can determine how much energy the wave has. For example, if you were to bunch these waves up, so you got more waves in a smaller space, you'd have more energy because you've got more waves. Also, if you were to make your wave much bigger, like this, and make it really tall, again, it would carry more energy. So these can both affect the energy carried by the wave. So very quickly, can you pause the video now and make sure you label in the peak and the trough, the wavelength and the amplitude, and just say what they are. One sentence. So the wavelength is the distance from one point on the wave to the same point on the next wave. The amplitude is the height. The peak is the top of the wave. The trough is the bottom of the wave. Okay, so pause the video and do that now, please. So longitudinal waves, just sort of introduce these. These are a bit funny, okay? So examples of this could be sound waves, slinky if you sort of push it back and forward, and again, some kind of earthquake waves. But the example you're most likely to find are sound waves. So if you didn't get that, add it to your table now. And the way longitudinal waves work is the oscillations are parallel to the direction of energy transfer. What that means is the wave might be traveling in this direction. So you can see here with the red arrow, it's traveling in this direction. But the oscillations are back and forth like that. Not up and down like a transverse wave as it goes, but kind of back and forth like that. Okay. So again, if you didn't get that, you're going to need to label it up now. So you'll need a diagram that looks a bit like this. Okay, so we might have in class used a slinky to show this. What you get with a longitudinal wave is where the waves bunch up, we call that a compression. Okay, and then after each compression, the waves actually stretch out a little bit. We call that a rarefaction. So what I would like to do is copy this up in your book, just like you did with the transverse wave. There is a couple of little other things I'm just going to add in for you. So let's just say we had a point on the wave. Let's just say here. So in the middle of the compression. The middle of the next compression is over there. So that would be our wavelength, because as you can see, it's in the middle of the compression there, and then the middle of the compression on the next wave. So I'm actually just going to label that up for you. That is the wavelength. Just do that in blue so it's really clear for you. There we are. So once again, can you pause the video, please, and just copy that up and make sure you've got that in your book, please. Okay, off you go. Okay, so in assignments, there is a copy of this worksheet. Now, this will probably take you about 15 minutes or so to do. Okay, so it will basically take you up pretty much until the end of the lesson. And then what you're going to do is, beginning of the next lesson, I will give you the answers to these questions. Okay, so if you need to, use the video again or go back through today's lesson to help you answer these questions. As always, I'll be online to help you, and good luck.